record now, okay? And so whenever you're ready, but still try to stick to 10 minutes. Here we go. We see your screen now. Good.
Okay. Oh, does it still show the column of the recordings or no? At the side, no?
No,
Okay.
no, I just see the, the NASA icon, the Lehman icon, and your title.
Okay, so yeah, just going over it again. So this was the title, semi-analytic framework to sending up a cosmic ray balloon into the atmosphere with the super pressure balloon.
Mm-hmm.
With Professor Enkardoki in the physics department. So the intro, well, it doesn't have too much here. It just describes what I was gonna do and how a full simulation is difficult to do without too much computing power, but we can base it off of the basic analytic framework.
Mm-hmm.
And this slide is, I was probably mentioning it a couple of times during the presentation about this graph. So in the top left corner, it was basically showing that the lower energy cosmic rays have a higher flux coming into the atmosphere. So that's what you see on the top left corner of the graph. It's more often, but the very high energy ones come in at a very, very rare rate into the atmosphere. It's actually in units of 1 event per square kilometer per century per steradium, but basically it's just very rare. And this comparison, when I was doing it with Serena Williams serving her tennis ball, is just that the same energy is basically applied to 1 proton. And when that happens, it goes basically at the speed of light. So that was that. Origins include, as I was saying, high energy events in space, including galactic nuclei, supermassive black holes, and starburst galaxies. This was that diagram I was talking about too, but unfortunately you didn't see it back then. So the detection of the cosmic rays was basically, you can see that there's this probe over there, the cosmic ray telescope high up in the atmosphere, and it can have a good angle to view the entry point of the cosmic ray into the atmosphere that produces the UV light and can be detected. So based on the analytical framework and support, what we want to find out basically is the arrival direction, arrival time, intensity and wavelength of the light emitted, and the physical processes involved from the arrival of the primary cosmic ray into the atmosphere are broken down into 4 steps. So the first one is the primary interaction with the cosmic ray, of the cosmic ray with the atmosphere. Then the evolution of the shower, so how it basically starts off a chain reaction, passing on its energy to the nitrogen atoms. The fluorescence production, when the de-excitation happens of the nitrogen atoms, and the fluorescence propagation that goes on back through the atmosphere into the telescope. So the physical model that we developed is divided into these modules. And the atmospheric one involved most of the calculation work out of any other one. So basically, it's set up the Earth as a geometric system, and based on that, you can set up the geometric altitude and the geopotential altitude, and then from that, you can have these parameters set based on the well-known equations from other research papers. You can, and Mathematica, you can do the temperature, pressure, density, number density. All those values can be used to make a plot of temperature versus height and pressure. Right, and that's just continued over here. Shower development module. So this one basically talks about the production function of quantifying the energy deposit from the cosmic ray per unit length along the shower track in the atmosphere. So, and that's what shows that chain reaction over there.
Mm-hmm.
The fluorescence module, well, fluorescence basically comes from the de-excitation of the nitrogen atoms, which make up 70% of the atmosphere, closely as an estimate, and just has some more calculation work here done. And most of the emission comes, as you can see, on the height and of the atmosphere. It's most of the emission is very high up in the atmosphere and comes in those wavelengths that are listed over there, around 350 nanometers on average. Yep. And the final slide basically here is just the future work. So I still need to work on the optical module and the detection module. And this topic can potentially answer the origins of ultra high energy cosmic rays, measure the energy spectra of them, and then prove on the knowledge of particle physics and expand on the standard model that I talked about a bit earlier. So one example is uh, detecting the delta plus plus baryons and just expand on the standard model that's studied in particle accelerators, which by the way, cannot accelerate particles to this speed nearly as nature can from space. And the final goal of this project is to actually send a full satellite into orbit to detect these ultra high energy cosmic rays. And yeah, that's basically it.
Yeah.
Mm-hmm.
That's fantastic. I'm glad we got to see it. And I believe some of your classmates and colleagues have stayed in the meeting. So maybe people have some questions.
Oh, okay, that's good. Okay, let me exit from this.
Yeah, I believe there are still 17 people here. So maybe somebody has a question they'd like to ask Anton or a follow-up.
Oh, it was probably a little bit more compressed than the first version when I talked about it, but um, some of the stuff I skimmed over than the first time when I talked about it.
Well,
But I can answer some questions about it.
yeah, exactly. All right, let's see if anyone has any questions. I see that there are several people still in the room. So just unmute yourselves, folks, and ask a question if you like. We have a couple of minutes now.
Mm.
Or people are feeling shy, perhaps. But this is great. Tell me what motivated you to do this particular project, to do, what interested you in this subject?
Well, Professor Nkardoki just kind of really wanted me to join this project, and at first I was a little bit hesitant about doing it, and then just I did some other research in the chem department, but I just came back to it, to be honest.
Yeah.
And I don't know, once I started doing it, I just found out I'm really interested in this project, and I look forward to finishing it next year. So in my senior year, I want to keep on working on it and yeah, see how it goes, because this project, it's part of a larger research group that is sponsored. Well, the grant comes from NASA, and my professor was saying that the PI for this research group amongst the scientists is in University of Chicago. So it's just interesting how this it's all part of a larger project, honestly.
Yeah. Yeah, exactly. It's like your piece of a much larger and ongoing project. That's fantastic. Well, thank you very much, and thank you for being willing to, to present a second time so that we have this full recording now. That's excellent.
Yeah, hopefully it was just as informative as the first time as I explained it, because some of the stuff I just kind of skimmed over the second time.
Hmm. No, but I think so. I think you did a lovely job, and it's an excellent presentation, you know, like PowerPoint as well. So there's a ton of information on each of your slides. And here's your, you're getting all sorts of love in the chat, as you can see.
Mhm. Oh yeah, I see it. Thank you.
Yes. All right. Well, thank you. I'm going to stop recording and keep up the good work, everyone, and everyone who's listening. You all did really great research as well. Thanks for being part of this. Bye bye.